velocity motion, dealing with Newton's second law with the F net equal to 0. This is Newton's second law. So in order to display the constant velocity motion, I filmed my brother sliding a cup across our table. This motion can be connected back to Newton's second law of motion with the net force, or total pushes and pulls, equal to 0. This is the clip of my brother moving the cup across the table. The origin of the axis is at the edge of the cup, halfway down the height of the cup. The length was calibrated by measuring the width of the cup, and the measurement of the position was kept constant by continuously measuring the position at the center of the middle Auburn logo. So from this, the initial conditions were found, which is shown here. So basically, the cup was massed, but in this specific case, the mass wasn't really significant to the motion model because the F net is 0. So the initial position and time, shown here, were used to calculate the average initial velocity, which is shown in this equation here. So the initial velocity is the change in the position vector over the change in time. So this was the second position recorded, and this was the first position, and this was the time between each frame. So our velocity vector in meters per second is given here. And so for this, so basically this is Newton's second law of motion. In this case, the constant velocity motion, the F net, right here, or the total pushes and pulls, is equal to 0. So because of this, that whole section right here is equal to 0, and basically the initial velocity is equal to the final velocity. So it's thus constant velocity. We created a model to depict this, to show how the cup moves. So basically it shows the motion in the negative x direction, which is correct according to the video. And on the graph, the line is straight with a constant slope, indicating that constant velocity is in fact present. So this was compared to the experimental data we got in Tracker graphically in order to tell if this is actually a good model or not. So here's the graph. It's the position versus time plots for the experimental data and the data generated by the model. In the plot, the x-axis is time in seconds, and the y-axis is position in meters. And so the blue dotted line is the experimental data, and the red line is the model. So generally, this is a pretty good representation of the motion. There are a few points where the model does not match the experimental data, which is basically here and then down here. So this is likely because of the limitations of the camera, because the video was filmed inside, but is actually in the middle section. This is more likely because like after some investigation, it realized that at that point during the video, the cup was sliding across part of the table where the varnish was worn off, and so this increased the friction, which made the net force non-zero and lowered the velocity for a few frames. So basically, how would this change things if the origin was placed at the edge of the cup in the last frame? After some investigation, there would be no change in velocity. Basically, just the position would change, and we can actually show that through some manipulation of our model again. So if we change the position and left the velocity the same, this is basically what it would look like, showing that the position would stay positive. So this brings us back to the question of what does all of this mean? Because the model worked relatively well, the F-net is 0. So this means constant velocity, basically. If you had created a model of the F-net as non-zero, it would not have matched nearly as well as this model did, proving experimentally that constant velocity is present when the F-net is 0.